Greetings, everyone. Now that we've talked about linear equations in two dimensions, take it the next half step up and talk about what happens when we have more than one of those. We call that situation a system. And there will be different situations where we might want to use this. One example would be later on when we study functions and we're interested in finding where two functions might meet each other. Okay? That would be an occasion where you'd have more than one equation in one problem. That's basically the idea of a system. I've got more than one different equation, okay? And I'm going to find out if these two equations intersect each other. So we're going to start with linear systems here. And there's only three possibilities when we're dealing with a linear system. The one that happens most of the time when you've got the two line equations is that they're going to meet in one spot. They'll just have one intersection point and therefore only one solution to the system. Okay, so a solution in a system means a single point, a single pair, that when you substitute it back into both equations, it makes them both true at the same time. Okay, of course there's a possibility of no solution, because we can have parallel lines that never intersect. And then also a special case along with the no solution is that you may have two different equations that look completely different, but they might represent the same line, right? And we've seen that sort of thing happen, you remember, because we can convert equations between different formats. We can multiply and make the coefficients look different and things like that, but it still represents the same line sometimes. So it is possible that the two equations in our system would actually represent the same line, in which case technically they're intersecting each other everywhere that they exist, right? So we call that an infinite solution, and typically we usually just display one of the lines as a solution set to the system, okay? There are three methods that I wish to present in this lecture. There's actually way more depending on which branch of mathematics you want to go down, but these three are the ones that apply to the algebra that we discuss in this course. Okay, the first is graphing. Now let me start out by saying graphing is not the most efficient method. However, it is awesome for someone like me displaying to you what's going on and to give you that good visual of what's happening, okay? Typically, though, we want to solve a system to find out where these two equations would intersect before we graph them to make our graphs more efficient. However, a quick graph, if you can throw some graphs up there pretty quickly, it can seem sort of efficient because you can get the x and y solutions at the same time. And it's sort of minimal actual, algebraic looking work. It's just a lot of drawing, okay? However, two major sources of error. One, if you're not using graph paper, which I'm using the closest thing I can on a marker board here, I've used a ruler to measure out the tick marks exactly. Even that still, I don't have all of the in-between lines, and even if I did, there's no guarantee that it would be 100%. So that's a possible source of error. And two, human error. A graph can only show you so much to our naked eyes, okay? If the answer is a decimal of some sort, like 10.27645. You're never going to be able to see that decimal on a graph unless you're already refining your graph to that many decimal places. Like if I'm making my tip marks, and typically we don't, it's very difficult to do that. Okay, so graphing is great for what I'm doing here, and you need to understand that this is a good method in case you fall off and don't have any other choice. But it is the least efficient method. Okay, so let me go ahead and show you why. You can see. So I'm going to graph these two equations. Since they're both in the general form, standard form, I'm just going to use their intercepts to graph them. That'll be the quickest way for me to crank these out. Okay, so my x-intercept remember, is when y is 0. So I'll do the little cover-up method here. My x-intercept for the top line, 2x, is going to equal 7. So that means x would be 7 divided by 2, which is 3.5. I'll write 7 over 2, though. 7 over 2, 0, is one of his intercepts for x. What about the y-intercept? If I let x be 0, notice I get y equals 7. So I'll have 0, 7 for that intercept. Okay? Let's take a look at the second equation here. For my x-intercept, if I do that cover-up method here, right, I'll have x equals 1. So in other words, 1, 0. And my y-intercept, right, if x is 0, I have negative 2y equals 1. So that would be 1 divided by negative 2. So 0, negative 1/2. Okay, so I'm going to graph these two lines now in these respective colors even, so that you can see that I'm using the red for the top equation and the blue for the bottom equation here, okay? So the top equation, I have 3.5 on the x-axis. So 1, 2, 3.5 is right here. Right here. And then 0, 7, 1, 2, 3, 4, 5, 6, 7 is right here. Alrighty. I will connect those 2 points. And of course, if you're doing this on paper, you still probably want to use a straight edge like I'm doing here. But on graph paper, you'd have a lot more success than what I'm doing here. Okay, next, I'm going to graph the other one. So I have 1 on the x-axis, which is right here, and negative 1/2 on the y-axis, which is right here. And I'm going to put these two together as best as I can. All right. Then the solution to the system is simply where the two lines intersect. So where does it look like they intersect? You can see right here, this is the point right here where they intersect. And it looks like 3 on the x, 1, 2, 3. And it looks like 1 on the y. Now, of course, that's me in my mind really, really wanting the answers to be whole numbers. All right, so that's number one big source of error, human error. I really want that to be a 1 on the y-axis, but I mean, is it really, or is it 0.9, or is it 0.95, right? The only way to be totally sure would be to take this and now plug it back in and check it. Because remember, if it's a solution, it has to make both equations happy at the same time. So you can do that. We can check it. 2 times 3 plus 1, right? If it's the 0.31 is my solution, equals 7, which is true, right? Because 2 times 3 is 6 plus 1 is 7. 7 equals 7, true. Check the bottom one. 3 minus 2 times 1 equals 1. That's 3 minus 2, which is 1, so 1 equals 1, that's also true. So 3, 1, x equals 3, y equals 1 is the solution to the system. I picked one that had whole numbers, okay? But it's very, very easy for this to not have whole number solutions. In that case, you're going to want to lean on the more algebraic methods, okay? This is a good method if you like graphing and if the answers come out to be whole numbers and you have graph paper and all of those, conditions. But mathematically, it is the least efficient number-wise, okay? Next, substitution. Solving by substitution is something that works across every branch of mathematics, okay? Substitution is going to be your solid rock of a method that if you like to see all the steps and you want to see where everything's flowing, this is going to be your guy. And even if it's not linear, when we do non-linear systems of equations, substitution is still a solid method that's going to stick around, okay? The idea is simple. If I can solve for one variable and get that, x or y, something is equal to some expression. Well, when things are equal, I can replace them for each other, right? So if I can just isolate one variable, that's step one, then I can use that value to substitute it in the other equation. And that's important. You're going to want to plug one into the other equation. Then that will give me something that I can solve. Okay? So watch. Same system. So we already know the solution. That's okay. I'll perform substitution on this one, and you can see we'll get the same answer. So I'm going to start by looking at my variables, right? I've got 4 choices here, 2 different x's and 2 different y's to perform step number 1. Because all it needs is just one letter by itself somewhere, okay? So what I'll do is I'll pick this bottom one right here. I'm going to add 2y to both sides. And that only counts in that bottom equation. I'm just focusing on that bottom equation. And what happens is I get that x is equal to 1 plus 2y, right? So I've isolated a variable. But what I've done is I've shown that x is equal, has the same value as 1 plus 2y. So I can take that 1 plus 2y and I can plug it into the x of the other equation. And that's what step 2 is. Take this thing that it has the equal value of and substitute it into itself in the other equation, right? Into x. So here's what happens. What I get is 2 times the substitution, because it's 2 times x, then plus y equals 7. This is still that same top equation there. I've just replaced x with something it's equal to. Now I distribute. Then I combine like terms. Subtract 2 from both sides. Divide by 5. So notice we got y equals 1. We already knew that it was supposed to be, right? So you can see that it is coming out the way it's supposed to be working. And then when I want to finish solving for x, I take the y value here and I resubstitute it, right? I substitute it back into the other equation because I've already got x solved for here. X is solved. I just needed some value of y to finish it off. So I'm going to take this y equals 1 now and substitute it back here. That's going to give me x is equal to 1 plus 2 times 1. And that's just 1 plus 2. So I get x equals 3. And therefore I have my solution. 3 comma 1. X is 3, y is 1. When you're dishing out the solution to these systems, by the way, you can either give it in x equals 3, y equals 1, the variables, or you could just give me the ordered pair 3, 1, because we understand as a mathematical whole that when you're given an ordered pair, it's x then y. Okay? Some people prefer to just write out the letters and just, for clarity. That's substitution. The other algebraic method that I want to present to you is elimination. Okay? Some people call it the addition method. It's always been called elimination in my lifetime, in my math classes that I was taught as a youth. So elimination is going to feel more like a magic trick. I hate to say that when we're doing math because none of this is really magic. It's just the method feels sort of mystical because it's all of a sudden everything just lines up and the answers just fall right out because you did a couple of little pieces of arithmetic. Okay? This method brings you a little closer to a branch of mathematics we call linear algebra. And most of the time, we prefer this method when we're doing linear equations, especially, just because it falls apart so easily, and you can really crank out the answers really easily, and some people can even, get a visual aspect of this one. Okay, so here are the rules. Elimination is more like a game. You can, in all different branches of math, you can add all different kinds of objects as long as they're the same kind of object, so that everything can line up in a like terms sort of sense. And what I'm getting at here is it's completely okay to take two equations like this and add them together. Right now, if I were to add these two equations together, I would get 2x plus x is 3x, y minus 2y is negative y, and 7 plus 1 is 8. And that's completely legal, right? I can do that. Add two equations to get another equation. And the reason why it's okay is because the two equations are in the same format. That's key. Make sure your equations are lined up completely, same format and everything, before you perform this particular method. Now, of course, this equation right here didn't get me anywhere. I still have something with both x and y in it, and I'm not going to be able to solve for one or the other immediately. So this didn't do any good, but it does show you what I'm going to do. I do eventually want to add equations together. I do have the ability to do it. However, I'm going to rearrange the equations a little bit first, individually, so that something will eliminate, something will go away and add to 0, in other words. Okay, so step 1, use multiplication. It's okay to multiply a single equation in a system. They're not tied together in such a way that you have to multiply them all at the same time. I can multiply the top equation by one thing and the bottom equation by something different. Okay, as long as you follow that golden rule of the equal sign, right? That equation by itself has the two sides, and you have to, do whatever you do to one side, do equally to the other type of thing, individually. Okay, so use multiplication to sort of change the system up so that when you do add two equations, something's going to add to 0 for one of your variables. Okay, so here we go. Right here, I'm looking at the y and the negative 2y. And what I'm noticing is that if I just had a 2y, a positive 2y, and added it to the negative 2y, those would add to 0 and eliminate, right? So all I'm going to do to make that happen is I'm going to multiply that top equation times 2. The whole equation times 2. And that's going to give me a new system. The new system looks like this. 4x plus 2y equals 14. And the bottom equation I didn't multiply by anything. X minus 2y equals 1 still. Okay. Now add those two equations together. That's the step 2. Combine the two equations. This is going to give me 5x. These two are going to add to 0, so they're gone. And then notice here I get 15. Solve for x by dividing by 5, and you'll notice that I get x equals 3. So elimination does feel smoother, quicker, more efficient, as long as you can see what you need to multiply right away. And it works a lot like LCD, when you're doing common denominator of fractions. Let's do it again, but this time let's do it on the x side, right? I'm going to eliminate x, and that's going to solve for y. Okay? So I'm noticing here that I have a 2x and an x. And I'm thinking, if I could just do 2x minus 2x, right? Okay, so to do that, what I would need to do is multiply this bottom equation times negative 2. If I multiply times negative 2, I'll get another version of the system where the top equation is still the same. So 2x plus y equals 7 is still the same. But the bottom equation is multiplied by negative 2. So I have negative 2x plus 4y, negative 2 times negative 2 is 4, right? And then equals negative 2 here. Now combine those two equations. These two are going to add to 0. I have 5y is equal to 5. And I divide both sides by 5, and I notice I get y equals 1. So again, same solution. We already knew that, right? We knew the solution is 3, 1. And anytime you get a solution, it's always best to check it like that. You know, just either mentally or on your paper, whatever. Make sure you're getting both equations happy at the same time. Okay? And then we have these two algebraic methods that are a lot more solid than the graphing one. Okay? Take a quick look at what this looks like in GeoGebra, and then we'll do more examples of these two algebraic methods.
Even though you've already seen it graphed, I just wanted to display it officially on a much better grid than the one I provided on the board. So the first equation was 2x plus y equals 7. There's the first line there. You can tell the intercepts are exactly like we did, 7 and 3.5 on the x. And then the other equation was x minus 2y equals 1. And again, your intercepts on that one were the negative 1/2 for the y and the positive 1 for x. And then of course you can see the two lines intersecting at the point we guessed at, right? And we actually checked it too, so we already knew that was the answer. Let's go ahead and make it official. The intersection is 3, 1.
Let's get another look at those two algebraic methods. I've got another system here, and we're going to work the same system again with substitution and once with elimination, so that we can get another example in here, okay? All right, so substitution, remember, means that I want to get one of the variables by itself. If you don't have one of your variables with a 1 coefficient, substitution can start to get a little bit messy, okay? But don't let that daunt you away from substitution. You just have to be ready to deal with a small amount of fractions, okay? Or decimals, you know, if that's what you prefer, but typically fractions. All right, so it really doesn't matter which one I pick. I am going to pick the top equation to solve for x, okay? So right here, 9x minus 5y equals 5. I'm going to add the 5y to both sides. And then I'm going to divide by 9. Okay, so I've got x equals 5/9 plus 5/9 y. This is going to be what I substitute into x in the other equation. So here I go. I have 4 times 5/9 plus 5/9 y plus 3y equals 18. I am going to distribute the 4. 20/9 plus 20/9 times y plus 3y equals 18. Now at this point you can, choose your own poison. Some people prefer to just go ahead and combine these, but to stay with, consistent with what we've been doing since we've been solving, I always showed you how we get rid of the denominator, so I'll choose that side. I notice the only denominators I have here are 9s, so I'm just going to multiply the whole equation by 9 times 9 to this whole thing. All right. Let's do it individually. Times 9, times 9, and times 9. Okay? So what does that leave me with? I have 9 over 9 is 1, so I have 20. Same thing, 20 with a y. 9 times 3 is 27. And 18 times 9 is 162. Okay, so I'm going to combine these like terms, but also I'm going to subtract 20 from both sides in order to get my letters on the left that I prefer to have. So I've got 47y is equal to 142. And I'm going to divide both sides by 47. Like so. Now let's think. 47. It's not divisible by 3 because 4 plus 7 is 11. It means it's also not divisible by 9 or 6. It's not even, so it's not divisible by 2 or 4 or 8 or 10 or anything like that. The square root is close to 7, so it would have to be something less than 7. And we've already gone through the whole list. 7 doesn't go into it either. So 47 doesn't break down into anything. And the closest this would get is, 47 times 3, which is not 142, right? More like 161, but okay, so this isn't going to reduce, and I'm going to leave it as such. Okay? Now 142 over 47, you may also, depending on the problem, maybe you're trying to locate this on a graph. So 142 over 47 is 3.02. 1, 3. So that was part of what I was talking about with the graphing method earlier. There's no way you could pick that off on a graph to be able to show the exact value that we could get with the 142 divided by 47 here. All right, let's finish solving the system. I'm going to solve for x now. So I take the 142 over 47 and I plug it back in over here. X is equal to 5/9 plus 5/9 times 142 over 47. And I can already tell that I'm not going to have a common denominator anymore because these both had a denominator of 9, but I'm about to multiply 9 and 47 here. So to accommodate that, what I'm going to do is multiply this left-hand guy by 47 over 47. Like so. Okay? So I'm going to multiply these. And what I get is 235 over 9 times 47. You know what I'm going to do? I'm going to leave that as 9 times 47 because I think it's going to reduce. Let's leave that as 9 times 47. Then 5 times 142 is 710. Yeah. So then I'm adding with the common denominator here. X is going to be 945 over 9 times 47. Oh yeah, look. 945 is 9 times 105, because 9 goes into 9 and 45 there. And then it's over 9 times 47. So I can reduce the 9s. And what I'm getting is x is equal to 105 over 47. When I divide that out, we get that x is approximately 2.234. So yet again, not something that I would have wanted to find on a graph. Okay? So that's substitution. Let's try the same system with elimination. Okay, so remember with elimination, what I'm going to want to do is get one of the variables lined up so that something will add to 0. Let me start with eliminating y. They're already negatives of each other, right? So I'm going to take the top equation, I'm going to multiply by something, and I'm going to do something different in the bottom equation so that the numbers line up. 5 and 3 both go into 15. So when I take the top equation and I'm going to multiply it by 3, and then the bottom equation, and I'm going to multiply it by 5. The result is going to give me 27x minus 15y is equal to 15, and 20x plus 15y is equal to 90. And then when I add these two equations together, the y's add to 0, leaving me with 47x and 105. So then I divide both sides by 47, and I get 105 over 47. Okay? So notice it's the same answer, right? Of course we expected that. Some people at this point in elimination prefer to say, well, it's quicker for me to just take this and plug it back in. I would say in this case, it's not going to be quicker than me doing the other elimination. So I'm going to start all the way back up at the top again, and I'm going to do another elimination now, but I want to make the x's eliminate. So 9 and 4 both go into 36, but I also need to consider that I need to make them opposite in sign. So I'm going to multiply the top equation by 4, and then I'm going to multiply the bottom equation by -9. The result here is going to be 36x minus 20y is equal to 20. Minus 36x minus 27y is then going to be equal to -162. And then I combine these two equations together. The x's eliminate to 0. I'm left with -47y is equal to -142. And then I divide both sides by -47. And of course the double negative becomes a positive, 142 over 47. So again, notice it's the same answer, but the workflow on the elimination side is so much smoother and more efficient because all I'm doing is just a couple of quick multiplications and then some division, right? Multiplication, addition, division. So it is going to feel like it flows better with elimination. Okay? Take a look at what this looks like in GeoGebra so that you can see the actual solution.
For this system, we didn't do any of the graphing, so I wanted to display it for you. The first equation was 9x minus 5y is equal to 5. The second equation was 4x plus 3y is equal to 18. And you can see right here where they intersect, not anywhere near a nice pretty line of any sort. And I have to zoom in a good bit for you to even be able to see, any of the decimals that even would be close. Trying to draw this by hand would be futile to have any sort of accuracy. Let's go ahead and have it calculate the intersection here. And as you can see, it's exactly what we calculated in the other two, the 2.23 and the 3.02.
To finish up this particular topic, we're just going to take a look at those two special cases that I mentioned at the very beginning of the lecture, whenever we have parallel lines or two equations that represent the same line. And what's going to happen is you're going to bring out one of your methods, If you do graphing, you'll notice immediately, because you'll either graph two lines that are, you'll see it, they'll be parallel, or you'll be graphing two lines and they'll land on each other. So the graphing method will be obvious. Substitution and elimination, what will happen is you won't have any variables left over, and you'll be left with either a false or a true statement. Okay, so let's do one of each. Okay, I'll do this first one by substitution and the other by elimination, so that you can see that it doesn't matter which method you do, they'll pretty much come out similarly. Okay, so here, I'm going to do this one by substitution. That means I'm going to take one of these equations and solve for a variable. To me, there's only one clear choice. I'm going to solve for this x right here because there's no coefficient. Okay, so this top equation becomes x is equal to 5 minus 3y, because I'm just going to subtract 3y from both sides in that equation. From here, I'm going to take the 5 minus 3y and I'm going to plug it back in to x. That's going to lead me to 2 times 5 minus 3y plus 6y is equal to 7. When I distribute the 2, I'll have 10 minus 6y plus 6y equals 7. And you'll notice right away the negative 6y plus 6y will zero out. So I'm left with 10 equals 7. Okay? So what's going to happen is in either of these cases, all of my variables are going to go away. And what I'm left with can either be completely true or completely false. As you can see, 10 does not equal 7, and this is false. So what this means is there's no solution. And of course, for a system to not have a solution means the lines never intersect, right? Parallel is the prognosis on that one. Parallel lines. Okay? Also, if you remember from my other lecture, I showed you a quick trick. You can tell that the slope here is negative 1 over 3. Again, negative 2 over 6 reduces to negative 1 over 3. They have the same slope, which means they're either parallel or the same line. So you know that that's coming right away when you look at the system. Okay, this one I'm going to do by elimination, but before you even look at it, I'm hoping you kind of see it, right? This one's sort of obvious. You can see that everything is double from one equation down to the other. These two are going to represent the same line, okay? But let's actually go through the method. What's going to happen is I'm going to say, hey, let's eliminate x, for example, right? So then my method would be like, okay, multiply the top equation by whatever it takes to match but do opposite sign. Great. That would be negative 2, right? Because negative 2 times 1 will give me negative 2, and that'll be the opposite of this guy. So then my system becomes negative 2x minus 6y equals negative 14 for the top equation. The bottom equation has been left alone. I don't change anything. Like so. Immediately when you add these two together, you'll notice the x's eliminate as we suggested. However, the y's also eliminate as a consequence. It's sort of like, oh wait, how did that happen? I didn't want that to happen, but you couldn't help it, right? If you change one, you change the other. And now the whole left side is just 0, right? The whole right side is going to be whatever it's going to be. In this case, it's 0. 0 does equal 0, which is true. If you land on a true statement, no matter which method you use, if you land on a true statement, that means the two lines are on top of each other. It's always true, in other words. Every single point is true for both. Okay? So what we do then is we have to say the solution set. And I'm going to go ahead and give you the most generic version of a solution set that we can get here, which is with set notation. Okay? So my solution set is the set of all, right? We do squiggly braces for sets. and my sets are ordered pairs, points, right? Each solution that's possible is a point. So I represent that with x and y. And then I put the little bar for the solution is a set of points that follow these rules, right? Such that, but what is it really following? It's on one of these lines, and they're the same line. So I'll just pick the top one. Such that x plus 3y equals 7. And then I close my squiggly here. So in other words, what this is saying mathematically is that the whole line is a solution to this system because they are the same line. They intersect everywhere, right? And this is just the dressed up tuxedo way of saying that this line is the whole solution set. Okay? All right, so go take a look at these two in GeoGebra, and I hope that this helps you in your solving endeavors.
So let's do these last two examples visually so that you can see what the math was telling us. In that first example, I had x plus 3y is equal to 5, and 2x plus 6y is equal to 7. And as you can see, these are completely parallel lines as far as where you can see here. And if I ask it to calculate the intersection, let's see what happens. See, question mark. There is no intersection of these two lines. They are completely parallel. Therefore, no solution when we solved our system. The last problem there was x plus 3y is equal to 7, and 2x plus 6y is equal to 14. And it looks kind of like one of the lines disappeared, doesn't it? Let me show you. I'll change the color on one of them to red. See, if I turn one of them off every now and then, you can see they are the same line. So that's why our system came out the way it did with a true statement. Let's see what happens when we intersect them. Again, question mark, because the computer doesn't know how to handle an infinite number of solutions. The solution to this system is, of course, one or both of these lines as a whole. So